So we did cover capacitors in an earlier chapter, but we assumed that the capacitors would actually charge up to their maximum value pretty much instantaneously, and that's really not the case. Capacitors, if they're hooked in series with a resistor, the resistor will actually slow the flow of current to the capacitor, and this will slow down how quickly the capacitor charges. Even a wire itself has some resistance, so no capacitor charges instantaneously. We did say that capacitors were very, very helpful because we could deliver a tremendous amount of power in a short amount of time. That's only if the resistance is low. If we have a capacitor which is in series with a resistor, okay, the resistor again is going to reduce the current, therefore it's going to reduce how much charge goes on the positive and negative plates. We can hook a system up like this where we have a battery or an EMF source, a switch, the capacitor, and then the resistor. And the time it takes to charge is related to what the capacitance is. Obviously, the bigger the capacitor, the more charge we can dump on it, and what the resistance is, because that is related to the current flow. When we look at the charging of a capacitor, we see that it charges like this. It's almost like taking an exponential and flipping it upside down. In fact, if we look at the form for this, the charge per unit time is equal to the maximum charge that the capacitor can take, according to the fact that the Q is equal to C times V, times 1 minus this exponential decay. So that's why it's flipped over in terms of an exponential decay. It's 1 minus this exponential decay. So it comes up to this equilibrium, or asymptotically approaches this equilibrium amount, where again it's the capacitance times the voltage. And we say that in this equation right here, again, you'll notice that this is a decaying exponential. RC is what's known as the time constant. It's the resistance in ohms times the capacitance in farads. And after one time constant, this becomes e to the minus 1, which brings us up to 63.2% of the charge. Okay? Basically, e to the minus 1 is 36.8, or 0.368, and that's why we get up to 63.2% of the charge. And after every other time constant, it's going to become additionally more and more charged. So again, capacitors do take some time to charge. We actually use this sometimes to create timing devices. Actually, it's a little more complicated of a circuit, but they use resistors and capacitors to help a 555 timer in digital electronics. I'm trying to remember back to when I took digital electronics. To produce a periodic signal. So in any case, after one time constant, we're up to 63.2% of the charge, and it would take an infinite amount of time to get all the charge, but asymptotically approaches, after a few time constants, you're up to about 99%. Once the capacitor is charged, after 10 time constants, you're at 99.9% charge. After it's charged, similarly hooked up to a resistor, it's not going to discharge instantaneously. That would be an infinite amount of current. Therefore, it takes time. Now it becomes an exponential decay. We start from its fully charged value of Q, and then it discharges exponentially. Okay? I should say, with an exponential decay. Again, tau is the RC constant, time constant, resistance times capacitor. The more charge that's sitting on there, the greater the capacitance, and also the greater the resistance, the longer it's going to take to discharge. So after one time constant, it's decreased to 36.8% of its original value. And again, it never exactly goes to zero, but it gets pretty close to zero. And after 10 time constants, it's pretty much, down to 0.001% of its original charge. We use capacitors again and RC circuits again for these digital timing circuits. They were originally used for these roadway flashers. In some cases, they're still used because it's such a simple circuit. A battery would power up and charge a capacitor. The capacitor would gain more and more charge, and then after it charged up to a certain voltage, it would send enough voltage across a neon lamp to break down the neon gas. It would flash. That would discharge the capacitor. It would stay lit. Then it would drop below the breakdown voltage, and the light would go out again, charging the capacitor. So it would blink, 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 and that would conserve energy because two things. One, if the battery's on all the time, this is just a glowing light. Okay? It would discharge much faster. Two, a flashing light is something that the eye is going to perceive much better, especially at night. So this served the purpose of doing that. Here's an example. Calculate the elementary properties of a simple RC circuit. We're hooked up to a 12-volt battery. The capacitance is 5 microfarads, and the resistance is 800 kiloohms. Find the time constant, so that's just R times C. Calculate the maximum charge on the capacitor. Maximum charge is C times E. Find the charge after 6 seconds. So we do this. The time constant is very simple. Here's our 800 kiloohms, 8 times 10 to the 5th ohms. Here's our 5 microfarads. The time constant is 4 seconds. Calculate the maximum charge. Q is C times V. There's our capacitance. There's our voltage. The best it can do is build up 60 microcoulombs of charge. C, find the charge after 6 seconds. Here's our equation for a capacitor, which is charging. Again, we're charging, we're not discharging, so we use the 1 minus the exponential decay. Plug in the numbers. This becomes 1 minus e to the minus 6 over 4, or e to the minus 1 1/2, and that becomes 60 times 46.6 microcoulombs. So you can see here, 6 seconds represents 1.5 time constants there. So again, it's mostly charged at that point.